Hi guys. Here's this is from the second handout, second note sheet, which is more about inference about means, about children's TV viewing. This is a relatively straightforward problem, except there's a couple little tricks here. You really need to read the problem carefully. It says at the beginning of the study, parents were asked to report how much television they watched in a week. How much did they watch in a week? And this is how much they watched in a week. Then they ask here to conduct a test, an average of more than 2 hours per day. Notice those are different units. So I'm going to set up my hypothesis, which is that the mean, and I'm not going to use the 2 hours per day. Well, I guess I will use the 2 hours per day, but I have to know that that is equivalent to 14 hours per week. Okay, so 2 hours per day, we'll use that. Mu is 2.0 hours per day. And then the alternative hypothesis, these must use the same values. It's greater than 2.0 hours per day. So now I'm ready to check my model. So independence, it doesn't state whether it's random, but we'll just say assumed. Hopefully researchers from Stanford would do that. Then we are going to check that yes, 198 students is less than 10% of all San Jose 3rd and 4th graders. So the independence assumption is met. We then would want to check, is it nearly normal? Now, we don't have the data, but we know that 198 is greater than 30 students, and so we can assume that it is nearly normal since the sample size is fairly large. We will therefore state we're going to use the student T model. We are using the T model because we have two sources of variability. We don't know the population mean and we don't know the population standard deviation. Then we will use a one sample T test. Okay, let's go down and start the mechanics. Remember that our T value, that's the first thing we want to calculate, is the statistic minus the sample, statistic minus the parameter divided by the standard error. So you have to have the same units, and so I'm going to use all same units. So I'm going to use hours per week for all my calculations here. So my statistic is going to be the 15.41 as the statistic. Then I'm going to use the 14 hours per week as my parameter, and then I'll divide by the standard deviation of 14.16 divided by the sample size, the square root of the sample size of 198, and that gives me a value of 1.40. And then what I can do is either use I have two options. I can use the stats and go to the test, or I can go to second distribution and I can go down to the TCDF distribution. So my X value is going to, clicked the wrong one. TCDF, that's 6, and I'm going to put in the 1.4 as my lower value. My upper value I'll put in as 1,000. My degrees of freedom, I'm going to put in the 197. And I do that calculation and I get a p-value of 0.08. So writing that, I can say that the probability of getting a t-value as extreme as 1.4 is equal to 0.08. Now, since the 0.08 is not less than 0.05, it is not as extreme as our alpha level, we will fail to reject. The conclusion is, since the p-value of 0.08 is greater than the alpha level of 0.05, we fail to reject. There is not sufficient evidence to state that children watch more than 2 hours of TV per day. Now, notice I said not sufficient. There is some evidence, right? Our statistic was that they watch 15.4 hours per week, which is more than 14 hours per week. So there is some evidence. Yes, they did on average watch more, but we don't have a sufficient level to come to that conclusion. Now, what if we didn't want to be this is children's TV watching. Do we really need to be at the 0.05 alpha level? If we chose to have a higher significance level, 0.1, then the 0.08 is less than the 0.1, so then we would reject the null. At the 0.01 alpha, there is sufficient evidence at alpha is 0.1 and a p-value of 0.08 to state, I think conclude would be a better word, sorry, to conclude that 3rd and 4th graders watch more than 2 hours of TV per week, 2 hours of TV per day.